So today I'm here to actually discuss the recent publication that Sarah led, the classification of hemoglobin fractions in the liquid state using a tool called Raman spectroscopy that we combine it with some machine learning tools for the chemometrics. So I'm going to start by this question: what happens after we eat? So I'm just gonna go to my happy place, which is when I ate souvlaki in Athens last summer. So what happens when you eat carbohydrates is that your blood sugar would rise, and then there are some hormones like insulin that are secreted in our bodies to actually, let's say, somehow bring that blood sugar down. That's what you're saying. So you eat breakfast or lunch, or yeah, you can eat souvlaki any time of the day. Then what happens is that the insulin takes the blood sugar down. Now, what happens if I eat a bit too many souvlakis? What happens is that these carbohydrates these carbohydrates that are digested and go into my blood would actually attach themselves to the hemoglobin. So these extra, let's say, sugars or for example, glucose attaches itself to the hemoglobins that exist in my bloodstream, and then creates something that is called glycated hemoglobin, which is one of the important let's say factors in blood for measuring blood sugar and an important factor in diabetes. Now, HbA1c or glycated hemoglobin is not the only hemoglobin that exists in our blood. There are naturally existing other type of naturally existing hemoglobins in our bodies, like normal hemoglobin, which is called HbA0, fetal hemoglobin, HbF, and HbA2. And other than these, there are also other types of hemoglobin that are not normal. They don't exist in a healthy blood. So these are different types that, for example, one of them is called sickled cell hemoglobin, or HbS. And there are many other types that might be, let's say, problematic, different than what we normally have. Now, the gold standard to detect the normal hemoglobins in the body, including HbA1c, is a technique called high-performance liquid chromatography, which separates the components of a sample, a liquid sample, based on their sizes, masses, or charges. Now, if these different components are separated in a specific way, when they come out of this chromatography device, well, you could see that over time, different sizes or different charges, different masses, they come at different times. So they come out at different times. Now, they know that, okay, the first one to be out is HbF, the second one to be out is the glycated hemoglobin, and so on and so forth. Now, if they measure it with absorption spectroscopy, we call it UVs, or they measure it with fluorescence, then they could actually say, oh, okay, I had like this amount of this component in my sample. Now, what happens if the case is a bit different and this person that we are measuring a sample of has, let's say, abnormal hemoglobin fraction? So, for example, sickle cell hemoglobin. What happens then? Then this device runs into a problem. And well, when you have extra peaks that might overlap with your normal hemoglobin peaks, their algorithms would actually, let's say, misfire. They might actually give you erroneous results for the naturally existing hemoglobins, and that is a problem. Now, there are alternatives or solutions to that problem, which means that, okay, I already used this chromatography device. Now I have to use a bulkier, more expensive device to actually say if my sample well, my sample has this amount of HbA1c or not, like to actually have a second test to see what is actually true. But at the same time, we could actually do a sort of a chemical fingerprinting of what is coming out of this chromatography device. Then we could for sure say that what is coming out and then, well, what we see, for example, in the left-hand blood is actually HbF or no. Is it HbF combined with something else? Is it like, let's say, I don't know, HbA, what was in the last slide? I forgot already. HbS. Is it like a HbS that exists now in my results? Well, in that sense, I know that whatever peak I'm looking at belongs to a certain category, a class, a fraction. Then I know that my, let's say, concentration measurements that I do with, for example, UVVs would actually correspond to that fraction specifically. So that brings us to the article that we got published, which had a main question: can Raman spectroscopy be the tool that can do the fingerprinting of these different fractions? Can it identify them, tell them apart, and not only say that, oh, okay, what I see has this specific concentration? So that's how we did it, actually. So we had our samples in a container in liquid state, and then we illuminated them with a laser of 785 nanometers, and then a fingerprint signature would come out of it that we analyzed to say which type of hemoglobin fraction it is. And the study is a feasibility study. Now, I said Raman spectroscopy, but what is Raman spectroscopy? So my sample has different types of molecules in it, different types of chemical structures. And these chemical structures, they have some bonds that could vibrate. And then these vibrations, they have certain energy states. So you have, for example, ground energy state, and then the ground energy state is separated into vibrational energy states and so on. And yeah, usually your molecules are in the ground state, but then when I send my illumination in, when I send my laser light in with a certain energy, then these molecules get excited. They go into a virtual higher energy state. Then afterwards, three things can happen. First is that the same energy is given back by the molecule. This we call an elastic scattering. So the same energy that went in comes out. The second scenario is that the molecule relaxes to a higher energy state than ground state. So now a photon of lower energy would be emitted. So this we call an inelastic scattering. And then the third scenario is that my molecule is already in a higher than ground energy state, and then it gets relaxed back to the ground state, and it releases a photon of a higher energy. And that is also inelastic because the energy has changed. So these two types of inelastic scattering is what we're interested in. And well, they're called Raman scattering. And when we send that Raman scattering through a spectrometer, what we get is a Raman spectrum, and what we do is a Raman spectroscopy. So yeah, this is the device that we use. This is the device that collects this scattering light and sends it to the spectrometer. And what we actually get out of this device is a spectrum that looks like this. Now, this is for a protein, but the idea is the same, that you have on your x-axis the changes in energy. So as I showed in the previous slide, yeah, so if it goes here, then you have this amount of change of energy. And if, for example, it goes to, I don't know, if it is excited from the second vibrational energy state and then gets relaxed back to the ground state, then you have like this amount of energy that is coming out. So let's say different shifts in energy from the energy that I sent in would be on the x-axis, and then how many photons did I get for each energy shift would be on the y-axis. So intensity versus energy shift in my inelastic scattering. Now, each energy shift corresponds to a change in the a change in the energy state, or when the molecule gets excited to a certain energy state and then comes back. So certain structures would have certain specific shifts that would have the peak there. Yeah. So, for example, if I have protein here, it would have this specific signature. Now, if I change it, for example, to silicon, to plastics, they would have a different set of peaks corresponding to the chemical signature of those materials. So what we did was to start studying these different hemoglobins, and HbA0 was the main normal hemoglobin in an adult human. So we studied the changes and the spectra. So on the right-hand side, you see that we have the HbA0, the normal hemoglobin, and HbS, the sickle cell hemoglobin. And you see that there is a subtraction between the two. That is going to be the case for the next slides as well. So there are going to be a comparison to the HbA0 normal hemoglobin. And the difference between HbA0, chemically speaking, the difference between HbA0 and HbS is that a building block called glutamic acid changes to valine, and then this change is the only thing that is different between these two structures, or the most significant chemical change between the two structures. And then how we can see it is a subtle shoulder in the case of HbA0. Yeah, so the black curve, you can see that here the shoulder is bigger than the hemoglobin, the HbS case. So yeah, you see that again. I'm gonna emphasize this a bit, that this is a very subtle change when you look at the whole spectrum. Now, if I look at HbA0 versus HbF, you can see that again, two of the building blocks are replaced by two other building blocks. And then the change again is a very slight one. So in the case of normal hemoglobin, you have this little peak here that you don't have it for HbF. In the third case, the only difference between the two hemoglobins, the two proteins, is the way that the chain of amino acids are folding together to create the hemoglobin. Yeah, so they call it secondary structure. So the only difference between them is how they fold, which again has some chemical meaning, of course. Again, you can see that in their OMID1 and OMID3 regions. These are just like the group of peaks that we call OMID1 and OMID3. So the only difference is in these two areas that correspond to the secondary structure of hemoglobins, these two hemoglobins. And the last one is the case of HbA0, normal hemoglobin, versus glycated hemoglobin. And there, the structure of glucose that is attached to the hemoglobin, the normal hemoglobin, it already exists in hemoglobin, in HbA0. And the fact that you have some additional chemical components added to the chemical structure would mean that one of the peaks would change its intensity. That in this case would be the case of HbA0 here. So HbA1c has some extra chemical components in its structure. So this peak gets a bit bigger. Yeah, so that's the only difference between these two structures. And our Raman spectra correspond to that as well. Now, we studied how the Raman spectra from these different hemoglobin fractions look like. We saw that the changes in them, the variations in these spectra are actually very subtle, sometimes even overlapping with the existing peaks of our hemoglobin spectra. Now we want to see if we can actually tell them apart, to cluster them, to group them together. Do they behave as such? So if I, for example, have my if I have my sample and I measure, let's say, 100, 200 spectra from it, from each one of these fractions, in the end, if I plot them all in a 2D plot, would they form groups? And this is the result of that grouping on the right-hand side that you see. So we used principal component analysis, which actually looks at the variations in your data in order to transform your system of coordinates for your data. For example, if you have a spectrum which has 1,000 data points in it, yeah, so it gets that 1,000 data points and then it translates them into some components called principal components that correspond to the variations in your data, yeah, the variances that you have in your data. Now, in that translated coordinates, how does my data look? Yeah, that's the question that we have here, and you can see that the 10 first principal components correspond to 84.9% of the variance in the data, and you see that the let's say the principal components, they have the highest variance for the first one, and then the second highest, the third highest, and so on. So PC1 corresponds to the highest variation in my data. And if you look at this 5x5 grid for the 5 first principal components, you can see that in this side of the plot, you have a certain grouping, a certain way of clustering that slowly dies, and everything comes into one big cluster. Now, if we want to look a bit closer at the clusters, so PC1 versus PC2 and PC1 versus PC3, you can see that there are actually some clusters, some groupings between the data, and you can see the labels of the data here. But you see that it's not 100%. Yeah, so if I look at, for example, HbA2, HbA0, you can see that here they actually overlap highly. But when I move on to here, you see that there is an overlap, but it's better. So there is a lot of information there with different principal components that you can actually use to somehow say that, oh, okay, my spectrum belongs to group HbA0 or group HbA2. Now, this is only for visualization, of course, that my data is not only defined by its variances, but also there are more complicated relationships and codependencies in the data that I can use to my own advantage to say, okay, if I have a new spectrum, to which cluster, to which group does it belong? So for that reason, we need a classification pipeline. So we don't only want the let's say clustering, we don't want the spectra alone, but we also want automation. So the classification pipeline goes as this. So first you need to prepare your data. Yeah, so you collect your data, and then you need to actually prepare it in order to to give it to a classification algorithm. Now, in the preparation step, you normalize the Raman spectra, you correct their baseline, you do artifacts removal, like, for example, spike removal or outlier detection, and other steps. And then when your spectra are ready, when your data set is ready, then you're ready to actually go to a classification model. Now, in this step that we want to work with a classification model, in this case and in this paper, MLP, multi-layered perceptron, or SVM, support vector machine. They have certain parameters that we need to sweep. They have certain hyperparameters that we need to tune, and then we need to validate and test them. And after we find a certain model that we are happy with, then we could actually deploy it and use it for our classification tasks. So this is the whole pipeline. So we start from the data and we get to the point that we are happy with our models. They're optimum enough as we go to deployment and classification. Now, the hyperparameters that exist in our models, for example, the number of layers, the number of neurons, learning rate, these are called hyperparameters. So if I give them set 1, they might give me a score or a test accuracy of 85%. If I give them set 2, they might give me 80%. Set 3, 92%. Now, how can I actually get a faster sweep? I can't really randomly put 3, 5 as the number for these hyperparameters and see what the score is. I can't do a sort of a random walk. I need to actually get to the result fast. And what I would do is to get these sets of parameters and feed them into a genetic algorithm. Now, a genetic algorithm is an optimizer that you start with a random state. Like, for example, you give it 10 sets of hyperparameters, and then you define a fitness function, which, for example, in this case, could be the score that you're getting from your model. And then these sets of hyperparameters could actually go through some, let's say, addition and crossover and mutation processes in order to become, let's say, new members of the parameter sets. So, for example, I start with set 1, 2, 3. Now, when I go through these 3 to 5th step, I need to select one of them to marry another one to make 2 babies. And then the 2 babies might be mutated. And then these new babies, these new creations out of these 3 sets, it might be that, for example, I take 3 and 256 and 0.1, and that would be my new parameter set. Then it actually goes back to the step of fitness evaluation. Now, this new baby, this new member, does it give me better results or worse results? So I analyze these things and I go through a feedback loop in order to converge to a point that my results wouldn't change anymore and they're maximized. And then I have my best individual, I have my best parameter set. So this is the way we actually go about the optimization of the hyperparameters and automate the optimization of the hyperparameters in order to have the best, let's say, classification using our spectroscopic data. Now, the optimization goes like this, that I define, again, the model's accuracy as my fitness. And now, for example, for a parameter set of 20 members, I have an average of about 75% and a maximum of about 95-6%. Now you can see that the maximum doesn't change a lot because, for example, if I have 20 random parameter sets, yeah, a lot of them would be bad, and that's why the mean fitness is so low. And then you might have some good ones in there as well. So the maximum is around this value. And then you could see that with generations, with the parameters making new parameters, the parameter sets making new parameter sets, I have an improved fitness, an improved model accuracy. And then slowly it saturates to a certain value, and then that's where I'm happy. Yeah. So for example, you in your algorithm, you say like, okay, if my model is not getting better after, I don't know, 5 generations and the maximum value stays the same, then you know that you should pull the plug. So yeah, that's the case for the optimization of the models, and you can have as many models as you want, and you can have any conditions on your hyperparameters as you want. You could have text hyperparameters, you could have integers, you could have floats, you could have continuous ranges, discrete ranges. So all of these could be actually implemented in the algorithm. And then what you would get is the confusion matrices. For example, for the case of these 5 hemoglobin cases, fractions, you would get this confusion matrix for PC plus SVM that you could see that, okay, 32 of HBS samples were actually classified correctly. And then you can see that, okay, these HbA2s were mistaken for HbS, yeah? And then only 3 cases happened that out of these more than 100 samples, you could see that, okay, only 3 cases happen to be erroneously classified. And then you have the same for the neural network, the multi-layer perceptron, that 2 cases are classified incorrectly. And then we actually do this classification multiple times in order to make sure that our random states, the decisions that we make along the algorithm that are a bit automated or randomized, they don't influence our results much. So you can see that we get a certain validation accuracy for the 2 models, so about 98 something % for the 2 models, and then a test accuracy that really confirms that, okay, how does my model work on an unseen test set. So finally, the decision is that our study has demonstrated the potential of Raman spectroscopy in identifying hemoglobin fractions in the liquid state, and then that would be the final conclusion of the presentation. Now, what is next? This work belongs to the European project called Vortex LC. That yeah, if you like what you see, and if you like to get more updates about it and some news about the project, and of course there are many other collaborators in it. So yeah, if you like seeing what's going on in this project, please do scan this QR code in order to connect to the project's LinkedIn page. All right, that's it. If you have any questions, I'd be more than happy to try and answer them.